So recall that in the last lecture, we did some representation theory and some homology. We saw what a projective cover of a module was. We saw what the projective presentation of a module was. So recall that if you have a module M, then there always exists a projective module that projects onto M. And if you take the kernel of this projective presentation, of this projective cover, you can take the projective cover of this kernel, and if you compose these two maps, you get a projective presentation. And today, what I would like to do first is to show you how you can lift these notions into the cluster category. And this will give rise to the notion of the index of an object. Okay, but before we do so, in order just to make sure that some of the tools that we're using in the cluster category are well understood, or at least known, I'd like to make a little reminder on what you can do inside a triangulated category. So I hope those of you who know triangulated categories will forgive me for doing this, but I would like to give a list of most of the axioms of a triangulated category and a list of most of the properties that we're going to use inside of them. So I will call this a reminder on triangulated categories. Even though it's only really a reminder if you've seen them before. Why do I want to say this? It's because remember that the cluster category of an acyclic quiver Q is triangulated. We've seen a lot of triangulated categories, for instance, in Bernhard's lectures for the derived category of a module category is triangulated. The cluster category is triangulated. So let's see what this means. Here's the definition. So a triangulated category, maybe I should say, for the moment, K is a field. At some point, it's going to be algebraically closed, and at some point, it's going to be the field of complex numbers. But for the moment, it's just any field. So a triangulated category, say T, it's going to be in this talk a K-linear category. So a K-linear category is a category where you have direct sums and where the space of, the set of morphisms between any two objects is a K vector space. And composition of morphisms is bilinear. So if you think of a module category, this is a K-linear category. In fact, all categories that we've seen in Laurent or Bernhard's lectures are all K-linear. So it's a K-linear category equipped with several things. So first, you need an automorphism, an autoequivalence, well, an automorphism really of the category, with an automorphism, well, a K-linear automorphism sigma of the category, called the suspension functor, and sometimes the shift functor. I'll try to stick to suspension functor, but sometimes my tongue slips and I say shift. So the two things are the same. And so that's one piece of information. The second piece of information you need is a collection of sequences of morphisms that one will call triangles. A collection of triangles a triangle is a sequence of morphisms of the following form. X goes to Y, goes to Z, goes to sigma X. Yes? I don't think it's to simplify, but... Yeah. No, I really want an automorphism. And in most cases, it's going to be an automorphism. If you had an autoequivalence, you could replace it. An autoequivalence, yeah, you could replace it by an automorphism, by chain. For instance, checking a skeleton of your category or something like this. Yeah. But I don't want to do that. I want to be able to take the inverse without having any second thoughts. And so this collection of triangles, the way you should think about it, and I'll try to make a very vague analogy. And so what we've done before was with module categories. Yes, you have an algebra, and you look at modules over this algebra and morphisms between these modules. This forms an abelian category. And what is an abelian category? Nice about an abelian category is that inside there you have exact sequences, short exact sequences. And these short exact sequences give rise, as in Laurent's talk, to long exact sequences of extension spaces. Yes. Now, a triangulated category is there to somehow take the information or contain the information of these long exact sequences. So instead of having short exact sequences, we'll have triangles which will play the role somehow of long exact sequences in a very precise way. It will take a little while until we get there, but let me list the axioms. So the first axiom is that there's a certain minimum number of triangles, if you will. If you take the identity morphism and you complete it in a sequence like this, then this is a triangle. For an object X. The second thing, for any morphism between two objects, any morphism F from X to Y, there exists a triangle containing F. And the second thing, somehow the class of triangle is stable under isomorphisms. So if you have any other sequence of the following form, X prime goes to Y prime, goes to Z prime, goes to the suspension of X prime, and if such a sequence is isomorphic to a triangle, then it is a triangle. Okay, so this axiom states basically that there's a minimal number of triangles in your collection of triangles. Now the second axiom says that if you have a triangle, you can... Oh, yes, please. So in some papers and books, people would say standard triangle instead of triangle, yes, or distinguished triangle. There are several competing terminologies, and I tend to favor the shortest one, so I simply say triangle. But what I mean is that if you have something like this, which is a triangle in my collection of triangles, and if I have another sequence of morphisms like this, I don't know whether it is a triangle or not, I just know it's a sequence of morphisms. And if I have isomorphisms, vertical isomorphisms, such that every square commutes, I'm sorry. Yes, you should write, so this, let's say this is x, y, z, and this here, it's not a C, it's an isomorphism, yes. And it's important that this guy is this, now I'm writing C. Thank you, Laurent. It's important that this guy is the suspension of this guy, yes. But if you have something like this, then the bottom row is a triangle as well. That's what is meant. For the moment, this category is only linear, so there is no notion of kernel or image. So we have no notion of exact sequences. But we are trying to have a setting where we can imitate this notion as best as possible. And these axioms will allow us to do so in a certain way. Now, in the second axiom tells that if you have a triangle, then you can deduce from this infinitely many triangles by rotating it. In fact, I should write it in a slightly more concise way. This sequence is a triangle if and only if the following sequence, which I will call the rotation, is a triangle as well. And I call this the rotation of this triangle for obvious reasons. Be careful of this minus sign. It will not really play a role in this talk, but it has to be. It's important in theory. Yes. And so it means that if you rotate once and then twice and then thrice and so on, you can create infinitely many triangles from only one. And you can rotate in the other direction by using the other implication. If this is a triangle, then so is this. And you can unrotate as many times as you'd like. Pictorially, sometimes people write triangles like this: F, G, H, and sometimes you put a plus here to make sure that we know that this is a morphism from Z to the suspension of X. Yes, sometimes I write this in this way, and sometimes I don't. Okay, this third axiom says that if you have morphisms of triangles, or rather, if you have something that is almost a morphism of triangle, you can always complete it into a morphism of triangle. So let's see. Say I have two triangles like this. And say I have morphisms small x and small y, such as this diagram commute. And so I can deduce a morphism here, which is the suspension of small x. Then there always exists, homomorphism small z such that the diagram commutes. So a category satisfying TR1 up to TR3 is called pre-triangulated. The triangulated category satisfies a fourth axiom, which has a very nice name, the octahedral axiom. Which I will not draw on the board. Oh, you seem disappointed. Oh. In order not to disappoint Bernhard, I will draw it on the board. So let x to y and y to z be two morphisms. In the category, and I will draw a picture. So here's f goes to y, and here's g from y to z. And I will complete this picture using the axioms that I already have as much as I can. And what do I mean by this? First thing, I have a natural arrow from x to z. I just compose f and g, yes. Okay, good. Now using TR1, I know that this morphism f can be completed into a triangle. Using again TR1, I know that this morphism G from y to z can also be completed into a triangle. Yes. There's a reason why I'm drawing these lines dotted, and it will become obvious in a moment. And now I'd like to complete this picture as well. See that I have a map from x prime to the suspension of y, and I have a map from the suspension of y to the suspension of z prime. I can compose them, yes? Okay, this is a morphism of degree 1. And finally, this map from x to z, using TR1, I can complete it into a triangle as well, yes? Now maybe I use a different color. And that's all the information for the moment that I can gather, or at least all the information that I want to gather. And what the octahedral axiom states is that there exist two morphisms, one here and one here. Yes, this is a nice octahedron, right? Yeah. Such that this morphism here is the composition of those two. So I'll just draw pictures to express what I mean. So this commutes. So this is this face here. This morphism here is the composition of those two. So this other face commutes. Yes. Now the face at the back, from z prime to y prime to x prime and back to z prime. So that's one thing. Another thing is that this is a triangle. And finally, see that there are two ways to go from top to bottom, yes? You could either follow this path, yes, this path, or you could follow the path at the back of the octahedron. These two are equal. So this commutes. And there are also two ways to go from bottom to top, yes? You could go on the left of the octahedron, or you could go on the right of the octahedron. And these two ways commute as well. Okay. So this is the most seemingly complicated axiom of triangulated categories. Why is it useful? It's useful in the sense that using TR1, we know that whenever you have a morphism, you can complete it into a triangle. And the octahedral axiom gives you information on what happens when you complete the composition of two morphisms into a triangle. An interesting fact is that it is still unknown whether TR4 is implied by TR1 up to TR3. Yes, please. No. Yes, that is the main problem with triangulated categories. So that is a good observation. For instance, here, this morphism is not unique. For instance, here, this triangle is not unique. So examples of triangulated categories that we've seen is derived categories. I'll come to this. But I don't want this lecture to become a course on triangulated categories. I have other things to say as well. So derived categories are triangulated. And the suspension functor is the shift. And this example is the reason why I sometimes make the mistake of calling the suspension functor the shift functor for an abstract triangulated category. And you can find a lot of triangles in the following way. If I have a short exact sequence in the module category, then you can deduce a triangle or rather, there exists a triangle of the following form in the derived category. So, if you'd like, yes. What I mean by this sentence is that if you give me such an exact sequence, I have an actual procedure to deduce a triangle of this form. Another example that we've seen, and the one which will be most important for this series of lectures, the cluster category. Recall that the cluster category is the orbit category of the bounded derived category, of the module category of the path algebra of the quiver Q. and you take the orbit category with respect to the action of tau minus 1 composed with the shift. Now, these axioms are a lot to absorb. It's a nice thing to play around with these axioms. I should say that even though the octahedral axiom seems a bit complicated, it is essential in most of the proofs of the results that we're going to state later. Now, what can you do? So I'll write this as a proposition. There are some things that should be known in order to play around with these axioms. So in TR1, this triangle here, yes, you have a morphism, you complete it into a triangle. This is not unique. But this object here is unique up to non-unique isomorphism. So first thing, so I'm in let T be a triangulated category. So the first thing, if you have a morphism and you complete it into two different triangles, so if you have two triangles that start with the same morphism, then the two triangles are isomorphic. Yeah, this is not X prime. Yes, thank you. Yes, exactly. You will apply this, and you will prove that if X and Y are isomorphisms, then Z is forced to be an isomorphism as well. And so for this reason, we will often call Z the cone of F. So that's one thing. And now the second thing is that triangles induce long exact sequences in certain abelian categories. So if you choose any object, I'll call it W, and if you have any triangle then you can obtain long exact sequences of vector spaces. If you apply the functor, the covariant functor given by hom W blank to this triangle, you get a long exact sequence of the form. So I will write, instead of writing hom CWX, I will just write WX because it will be shorter. Hom W to Y, hom W to Z, hom W to the shift of X. And now recall that if this is a triangle, then all of its rotations are triangles as well. So I can continue this sequence by applying hom W blank to the rotations of the triangle. And I can continue like this. And of course, rotations go both ways, so I could come from this side as well. And I get the long exact sequences of vector spaces. Sorry, my category T, my triangulated category. I should change this as well. Thank you. Now the third property is the same, well, a dual property. If you apply the contravariant functor Hom blank W, then you get a long exact sequence going in the opposite direction. And these properties are the ones we are going to use. Now, I'd like to note that all of these vector spaces, these Hom spaces from W to T, whenever you have your morphism, say here, from W to X, you can always precompose it with an endomorphism of W, and you will get a new morphism from W to X. So this long exact sequence, this space here is actually a module over the endomorphism algebra of W. And this long exact sequence is a long exact sequence of modules over this endomorphism algebra. So a long exact sequence of and W modules. Right. And W modules. And the same is true here, yes? If you look at the morphism from Z to W, if you post-compose with an endomorphism of W, you still get a morphism from Z to W. So this is a left module over the endomorphism algebra of W. So again, here, this is of left modules over the endomorphism ring of W. All right. So if you do something like this, you can prove that this is the same as this. So, yes, so if you have, let's see. You want me to define multiplication? Yes, it's composition. So if I have a morphism, say phi, in Hom from Z to W, and if I have a morphism, say F, from W to itself, then you can see that if I first apply phi, so that goes from Z to W, and then I apply F from W to W, this gives me a morphism from Z to W. And this is the left module structure of this space over this algebra. Okay, so this is a lot of tools that one can use in triangulated categories. And what we're going to do now is we're going to apply them to our special problem. Recall what we want to do. So this is a lot of things. Let's put them aside and remember what we're trying to do, right? We saw homological algebra. We saw projective presentations of modules. And I started this talk by saying that we want to lift this to the cluster category. So now we know what tools we can use inside the cluster category, because all of this is true in a triangulated category. So we'll use this to define an analog of projective presentations. And this will be called the index of an object. So where will I be? Let Q be an acyclic quiver. And then I will work inside its cluster category. And inside there, I need, so the cluster category categorifies a cluster algebra, yes? And in a cluster algebra, you have an initial seed. And the equivalent of the analog of an initial seed inside the cluster category is an initial cluster tilting object. These were defined in Bernhardt's lecture. So let T, T1 up to Tn, be a cluster tilting object. In CQ. And what does this mean? It means that T is rigid. So there's no morphism. Its suspension. Well, no non-zero morphism from T to its suspension. And T is maximal with respect to this condition. So if you have another object that has no extensions with T, so that's such that this vanishes, then this object X looks a lot like T. It is a direct sum of direct summand of T. And for example, you can take T to be the image in the cluster category of the algebra itself, the path algebra. Or you could take T to be any of its suspensions. Yes, because these two conditions remain true if you take any suspension of T. Oh, sorry, add T is the set. So if T I write in this way, so I'll say that it's basic. So I mean that Ti and Tj are not isomorphic to each other if I and j are not equal, and all Ti's are indecomposable summands of T. So the cluster category is Kohl-Schmidt, yes? So if I take any object T, I can decompose it into a direct sum of indecomposable objects. And this is what I do here. I fix one such decomposition, and I call the direct factors T1 up to Tn. So add T is the set of all objects of the form direct sums of these Ti's. When I write a power to an object, I mean you take this object, you take a direct sum of AI copies of Ti. And as in Laurent's lectures, n contains 0. And so this is what I start with. And in the same way that in any module category, any module admits a projective presentation, in such a cluster category with a cluster tilting object, any object will sit in a triangle that looks very much like a projective presentation. So let me write down the proposition here. So for any object X in CQ, there exists a triangle, say T1 of X goes to T0 of X goes to X, goes to the suspension of T1 of X, where T0 and T1 are in add T. So that's one thing. Maybe a second thing I would like to say, and I should have said this first really, but I just remembered about it now. Remember that we said in a cluster category, you have the path algebra that appears somewhere, you have all the modules in the cluster category, and then you have copies of the shifted and decomposable projectives. And if you kill them, if you take the quotient by the ideal of morphism, factoring through the shifted projectives, you get back the module category of your path algebra. This is true in a more general setting. So the functor, the following functor, I'll call it F again, but this time I take extensions with T. So if I replace this blank by any object X, I get a right module over the endomorphism algebra of T. So this induces an equivalence of K-linear categories. So F goes from CQ into, I should give me some space here, into the category of right modules over the endomorphism algebra of T. Yes. And since T is rigid, T is sent to 0. And this defines the kernel of this functor. So if you quotient out by the ideal of all morphisms factoring through anyone in add T, you get an equivalence. We have seen this already in the special case where T is a certain shift of the path algebra KQ. I just want to say that this is more general. Now a remark. I want to remark on this triangle. I want to say why this is a lift of a projective presentation into the cluster category. So how, in practice, how do you compute this? So the first thing, maybe if X is in add T, then this triangle is easy to compute. If, say, if X is Ti, then how can you find such a triangle where X is Ti and those two terms are in add T? Well, here is one. Take the identity from Ti to itself. This is in add T by definition. And complete this into a rotated triangle. So you can put a 0 here, and the suspension of 0. The suspension of 0 is 0, yes? And 0, of course, is in add T, yes? It's the object where you put all AIs equal to 0. So if X is one of the TIs, then it's easy to compute this triangle, or one such triangle at least. Second thing, if you know such triangles for two objects, then you know one for the direct sum. Yes, you can take the direct sum of triangles. So if T1x to T0x to x to the summation of T1x and T1y to T0y to y to sigma T1y are two triangles, as in the proposition, then you can take the direct sum. And of course, since all these four objects are in at T, then direct sums of these objects remain in at T. The third remark I want to make is that one should be careful that the triangle in the proposition exists but is by no means unique. So the triangle in the proposition is not unique. And I'll give you a almost stupid example to show that this is the case. If you take x to be the zero object, then I will give you two triangles as in the proposition. The first triangle has zeros everywhere. So this is x, and these two objects are in at T. And if I take, say, T, the identity goes to T. I know by TR1 that if I complete this into a triangle, then the next term has to be 0. So this is x, and these are in at T. So this is also a triangle satisfying the conditions of my proposition. So the triangle in the proposition is not unique. And finally, I promised an analogy with projective presentation. So here it comes. Let me take an object, say incomposable object in the cluster category, call it X. And I would like to compute its index. Sorry, I'm thinking ahead of myself. I would like to compute such a triangle for X. I know how to do it if X is in at T, so let me assume that it's not. Okay. So what I'll do is I'll send X into the module category of the endomorphism algebra of T using my functor F defined over there. So consider the functor F from the cluster category to the module category of the endomorphism algebra of T. Notice that, so of course, anyone in at T is sent to 0 because T is rigid, but anyone in sigma minus 1 of T is sent to a projective module because it is sent to a direct factor of the endomorphism algebra of T as a module over itself. All right? So by the proposition, I have a triangle like this. With T1 and T0 in add T. I want to compute them. I want to have a way to compute T1 and T0. And what I'll do is I will apply this functor to this in order to obtain a long exact sequence. So the first thing I will do is I will apply the inverse of the suspension functor to this triangle. So this is still a triangle. Now when I apply f to this triangle, I will get a long exact sequence. And this guy is in add sigma minus 1 of t. So it's going to be sent to a projective module. This guy is going to be sent to a projective module as well. And finally, this guy is in add t. So it's going to be sent to 0. And I have a long exact sequence. So let's apply f. Then I get f of sigma minus 1 of t1 of x goes into f of sigma inverse of t 0 of x to f sigma minus 1 of x to 0. And this is exact. And this guy here is projective. And this guy here is projective as well. And this is a module over the endomorphism algebra of T. So this sequence is a projective presentation of this module. So let's do this in reverse. In order to compute T1 and T0x, compute this module. In most cases, we can do that. Compute its projective presentation. We know that we can do this. We've seen examples on the Kronecker quiver. And once you have the projective presentation, you look at what projectives appear here. This will give you which summands of T appear here. You know what projectives appear here. This will give you which projective summands of T appear here. So, thus, to compute this triangle, it suffices to compute a projective. Let's take it minimal, because we can do it. Projective presentation of the module f of sigma inverse of x. I promise that there will be examples of such a computation over the Kronecker quiver. I only ask you to wait until the next lecture to see one. And the next lecture is this afternoon, so it won't be so far away in time. So, two important things. If you have a cluster tilting object, then you can find such a triangle, let's say a presentation of any object x by add t. That's the first important thing. And the second important thing if you apply F, this sequence, or rather a shift, a suspension of this triangle becomes a projective presentation of a module. So if you know how to compute projective presentations of modules, then you know how to compute this kind of triangle. So this is always a kind of idea. Yes, the cluster category seems very complicated. It's triangulated, it has many morphisms, but anything we're trying to do inside the cluster category, we cheat by going into some module category and then coming back. Yes. Now I said that the triangle in the proposition is not unique, and this is true, because we have a counterexample here. However, a certain quantity is invariant in here. So I'll write this as a proposition. So let X be an object in the cluster category, and let T1x, T0x, x, suspension of T1x be a triangle as in the proposition. And even though this triangle is not unique, a certain quantity is. So this quantity, where will it live? It will live abstractly in the growth in D group of the additive category of T. Or what is this? Yes, this is nothing scary. It's just a free abelian group generated by symbols that correspond to the decomposable direct summons of T. So an element in here you can view as a vector of integers, and integers in a vector, yes? And what will it be? So if you take the image of this in this growth in D group, T0 of x, and you subtract the image of T1 of x, then this doesn't depend on the triangle that you've chosen. So this does not depend on the choice of the triangle in the proposition. So if you want to see what this is, yes, you can say T1 of x and T0 of x, these are elements, objects in add T. And objects in add T already? Oh, no, I still have 15 minutes, is that right? Okay. So these two objects are direct sums of T1 up to Tn, yes? So let's say that this one is a direct sum of Ti to the power Ai. And let's say that this one is a direct sum of Ti to the power Bi. Yes. In this case, this element here, if I want to view it as an element in here, it is going to be the sum of Ai minus Bi times the representative of Ti. So if you want to view this as a vector of n integers, the ith coordinate is Ai minus Bi. And this does not depend on the choice of triangle. Now, if you go to our... Okay, thank you. Okay. Another thing I want to mention is that the index of a direct sum of objects is the sum of the indices. And this is because of the remark that I've just erased here concerning the triangles associated to direct sums of objects. Oh, I forgot to do the stupid example. The index of the zero object is, of course, 0. And how would you compute the index of any object? Yes. So here's what I'm saying now is a kind of a way to summarize what we've done until now. If I give you any object x in the cluster category, and I say, please compute the index, what would you do? If possible, first, you decompose x into a direct sum of indecomposable objects. That's the first thing. Second thing, for each of these indecomposable objects, look whether they are in add T. If they are, then they contribute such a vector to the index. Okay? If they are not in add T, apply F and send them into the module category, and there compute a minimal projective presentation. This minimal projective presentation will give you the index of this direct summand of x. And once you've done this for all direct summand of x, you apply this remark. You take the sum of all the indices that you got, and this gives you the index of x. Now, of course, in practice, this is not always easy to do, yes, because it requires some computations in a module category. However, what I mean to say here is that it allows you to do these computations without any other tools than module categories. All right. So in about 7 minutes, I can introduce maybe some of the things in the next section. We will continue after lunch, of course. But so now we've seen that if I give you an object in the cluster category, you can compute its index. It's a nice vector of integers, positive and negative. It's possible that different objects have the same index, so it's not a complete invariant for isomorphism classes. Still, it's kind of the soul of the object that we want to keep in order to categorify cluster algebras. So let's see what I mean by that. So second section of this talk, we'll talk about cluster characters. Cluster characters have appeared already in different lectures, those of Laurent and those of Bernhard. So they will appear now in my series of lectures. From now on, I work over the complex numbers. And the reason for this is not because the algebra doesn't work, but it's because there will be Grassmannians involved. And I want these Grassmannians to be complex varieties so that I can compute their Euler characteristics. So Laurent has defined cluster characters or Calderot-Chapoton formulas for modules. He's given a formula for them. I will give an equivalent but slightly different formulation of this formula. I will call it cluster character because I'm used to this terminology. I will call it the CC map most often. So if you prefer Calderot-Chapoton map, it's the same initials. So you should be fine. I will do this in 2 steps. First thing, I will define something that contains less information than the cluster character, and I'll call this the F-polynomial. So the F-polynomial you can define for any module over any algebra. So what I'll do, I think, is I'll give the definition, write down the formula, then we can have lunch. And then the first thing I'll do after lunch is I'll write down the formula again, and we'll continue from there, okay? So bear with me for 5 more minutes. So let A be a finite dimensional K-algebra. So this means in particular that A, I will always view it as the path algebra of some quiver modulo some ideal of relations. Let M be a module over A, finite dimensional. Then the F polynomial of M is defined as follows. It's going to be a polynomial in n variables, y1 up to yn. And it's going to be a kind of cheap version of the formula that Laurent showed us when he wrote the Calderot-Chapoton formula. So Fm of y1 up to yn is going to be a polynomial with integer coefficients in n variables. An actual polynomial, not a Laurent polynomial. Yeah? And how do you define it? So look at your module. And you want, in some sense, to have a kind of generating series counting all possible submodules of M and grouping them with respect to their dimension vectors. So we saw that if I give you a dimension vector, say E, you can construct a projective variety whose points are in bijection with submodules of M with dimension vector E. This is the, how did you call it? Submodule Grossmannian or quiver Grossmannian. Or Grossmannian of subrepresentations, I remember now, yes, that Laurent has defined. So Ger E of M. So Ger E of M is the submodule Grossmannian of M for dimension vector E. It is a complex variety. For all of these varieties, we want to count points, yes, but there are infinitely many points in each of these varieties. You can't do that, so you need to measure the size of these varieties, and the measure that we choose is the Euler characteristic. So take the Euler characteristic. Laurent has given nice tools in order to compute Euler characteristics. The Euler characteristic of the empty set is 0, of a point is 1, of an affine space is 1, of a projective space Pn, it's n plus 1. If you have two disjoint constructible subsets, then the Euler characteristic of their union is the sum of the Euler characteristics, and so on. And you take the sum of all these multiplied by a monomial given by the dimension vector. And here when I write y to the power of e, I really mean y1 to the power of e1 times y2 to the power of e2 up to yn to the power of en. So in this formula, I have all the information of all the sizes of all submodule Grossmannians of my module M. Thank you. And that's the definition. Exactly. Exactly. So it is a generalization of the usual Grossmannians. Yes, the usual Grossmannian we're used to, GKN, is a variety whose points correspond to submodules of dimension k, sub-vector spaces of dimension k in a vector space of dimension n. Yes? So here it's a generalization. But instead of parametrizing things by dimension of submodules, I can do something a bit finer, and I parameterize them with the dimension vector. Thank you for that. Small n is the number of vertices in the quiver, the Gabriel quiver of Q. So this should, I hope, remind you of the Caldero-Chapotin formula that Laurent has given in his lectures. But it should also be clear, I hope as well, that it's not the same, yes? Because in Laurent's lectures, the Caldero-Chapotin formula is not a polynomial, it's a Laurent polynomial, yes? We will transform this into a Laurent polynomial later today. So thank you.